there exists so we have this functional calculus 1 sub e of x e in Fourier set of the line. For every Fourier subset of the line, one has a spectral projection corresponding to this thing, and which is going to be, in fact, and these are the so-called family of spectral projections are uniquely determined by x. Right? In the sense that x can be written as, if you approximate the function f of t equals t by simple functions, the corresponding linear combinations of the spectral projections will converge to x strongly. Right? And such a family is unique also. It is the functional calculus. There is a one-dimensional algebra generated by x is exactly you got to look like an infinity of of the spectrum with something, and in the projections in that one-dimensional algebra are exactly these shapes. The projections in L infinity are exactly the indicator functions, and so their images are precisely the projections in the. This family of spectral projections it's canonically determined by x. So what I mean by canonical is okay. See, we proved that for a one-dimensional algebra, it satisfies this double commutative condition, or this characterizes one-dimensional algebras. Star algebras satisfying this condition are precisely the one-dimensional algebras. And if M is a one-dimensional algebra, so is M prime. M prime also satisfies M prime equals M triple prime. And so there is a kind of duality in the theory of one-dimensional algebras, M and M prime. If you can take larger M, the primes get smaller and so on. Okay, so I want to say let x and let x and b of h. I want to say the following are equivalent. See, I am just making one very simple observation, that if a one-dimensional algebra is generated by some family of some set of operators, then something will commute with everything in the one-dimensional algebra precisely when it commutes with everything in the generating family. Okay? So in particular, we've shown that we've shown that let me recall the following fact. If you take the space of projections in M, in fact the non-closed subspace, let alone the strongly closed subspace, is itself equal to M. Right? And also this is the class of projections in M, this is the class of unitaries in M. Although U in M, so then U star U equal to U star equal to 1. So consequently, X is in M if and only if X commutes with E prime for all E prime in P of M prime. Right? M prime is a one-dimensional algebra. So it is going to be spanned by its projections. So something is going to commute with everything in M prime precisely when it commutes with every projection in M prime. Right? It's the same thing for unitaries. I can write the same thing for U prime and M prime. But which I'll write, okay, the same thing. Right, by the same reasoning. But this is equivalent to, because U prime is invertible and the inverse is that they are joined, this is equivalent to saying that U prime X U prime star equal to X prime for all U prime and M prime.
Equal to X.
Equal to X, sorry. The moral of this story is the following thing. See, if you take any unitary operator on H, you take anything in U of B of H, let alone U of M prime, then conjugation by, so we know that in fact if you start with a unitary operator on H, say U, from this U you can associate something called add U, which is an element of ought B of H. Ought means automorphisms. The automorphisms of B of H. That is, it preserves all the structure of B of H. B of H is a vector space, it has product structure, it has adjoint structure, it has various topologies. This thing preserves each of those things. It is a W star homomorphism. It is a product preserving map, it is a star preserving map, it is a one preserving map. Everything it preserves. And this add U is the map which sends, this is the map that sends UX U star. Add U is the mapping defined by sending an X to UX U star. In fact, one can even see that this map U going to add U, I think I gave this as an exercise before, did I not? That if you take the map U going to add U, that is a group homomorphism from the group of unitaries of B of H to the group of automorphisms of B of H. That is, if you take add of U1, U2, that will be the same as add U1, add U2. Okay, anyway, what I am trying to say is that, see, the maps of the form add U, these are all automorphisms of B of H. They preserve all the structure. So the moral I'm trying to get at is whenever you have a theorem which says that something is unique, then under automorphisms, they will carry those unique things to the unique things. So what I mean is a kind of meta theorem I'm saying. So for example, if x equals V mod x is polar decomposition in place, add u x equals add u of v times add u of mod x is the polar decomposition. Right? So what am I saying? If x equals v mod x, then because add u preserves products, it follows that add u of x will be add u of v times add u of mod x. Because add u preserves all the structure, add u of v is going to be a partial isometry, and add u of mod x is going to be positive, and both of them will have the same kernel because v and mod x have the same kernel. See, what is the kernel of add u of x? In general, if you take an x and if you take add u of x, that is ux u star. Who will be killed by ux u star? When will ux u star of xi be 0? When u star xi is killed by x, because u is invertible. So xi is 0 if and only if xu star xi is 0. That means xi is in kernel of x if and only if u star xi is in kernel of ux u star. That means if you read it the other way, this will say that u of kernel x equals u of equals kernel of add u of x. The xi's which are here are exactly those. If you take u of things here, xi is here if and only if u xi is here is what I am saying, which is obvious. xi is 0 if and only if ux u star of u xi is 0. So, if in the polar decomposition all these three guys are the same kernel. So if you apply add u, then you will have the kernels of these three guys will be u of the kernel of this, u of the kernel of this, u of the kernel of this. So they must all be the same. So by uniqueness of polar decomposition, you will conclude that add u of x equals add u of v times add u of mod x. So the meta theorem I'm trying to prove for you is that if you take any canonical operation on elements in a one-dimensional algebra, that means those things which will be respected by all automorphisms, then you will never get out of the one-dimensional algebra. So I'll give you one more instance of this. Here I said the spectral The family of spectral projections of X are unique. Right? So the same thing will say that, for example, add U of one E of X is what? U, 1E, U star of X. Which is what? This is the projection. See, if you take U1, if you take a projection P and you take UP, U star, a projection is determined by its range. So what is the range of UP, U star? You take UP, U star and apply it to any vector xi you want. The range of UP, U star is all UP, U star xi. All U star xi is the same as all eta. So the range of UP, U star is the range of is the set of all UP eta, which is U of the range of P. Right? There is a projection onto the range of U of 1 of B, E of B. So now what I want to say is this is the same as, by uniqueness, this is equal to one U E U star X see what is the range of this? It is going to be U of no, I'm ready some answer. U1E U star. Sorry. Yeah, see what is this? Projection onto U of any subspace is, I said, see the earlier statement that I made, actually what I was trying to say, I said about in kernels. So I want to say range of UP U star, suppose P is the projection. What is the range of UP U star? It is just range of UP, which is the same as U of range P. Right? So I am saying we take U of 1ex of H, that is U of range 1ex, that is exactly the range of, this is the projection U 1ex U star. I am saying same thing in no. Sorry, I'm making some groups. Let me start again over there. So, see what I'm trying to say is that see, automorphisms preserve any natural operation. So what I mean by saying that is, on the one hand, you can take x and set E, and you can associate the projection 1E of x. This is a certain natural operation. On the other hand, you can take the same E but apply the automorphism. So I'm saying E and this will correspond to U 1EX U star. That is, I am saying that this is equal to 1E of UX U star.
What is the range of 1EX?
Huh?
What is the range of 1EX?
In terms of E, to describe that is if E is an interval, then you can possibly describe the range of 1E. No, I want to just choose the fact that this association of spectral projection to a self-adjoint operator is completely canonical. What I mean by canonical is, when I apply an automorphism to X, the associated thing will be applied by applying the automorphism to that associated thing for X. That means if we take 1E of U, I'm saying that X going to 1EX is canonical. What that translates into, and you can sit down, verify it whichever way you want, is the statement that 1E of UX U star is going to be exactly U 1EX U star. See, we have this measurable functional calculus. It is the unique homomorphism from L infinity of the spectrum to bounded operators which carries the function t to x and is appropriately continuous. Right? Now you apply that condition, you can see that this is true. If you look at the map, that sense, so what I'm saying is that for any f, I'm trying to say that f of ux u star will be u fx u star for any measurable function. I want to apply, so you can prove this by the uniqueness of the functional calculus. Functional calculus is a unique map that sends the function, identity function of the spectrum to 1, identity function of the spectrum to x, and is appropriately continuous and is an algebra homomorphism. Now both functions will carry the identity function of the spectrum. Spectrum of x and spectrum of ux u star are the same. So that function, if I call that function t of ux u star is going to be ux u star. It is just the identity function on the spectrum. And and f of x is going to be just x, just as f of u x u star is going to be I'm saying making undue fuss over this. Okay, we'll get back to this. Let me get this clarified in my head. I'll just make more of a mess of it. I'll continue. The point, at least, I've tried to explain in the polar decomposition example. Because the polar, if you take V mod x, the partial isometry and the positive parts of the polar decomposition are uniquely determined by x modulo certain properties, which are just Hilbert-Swear's properties. Now, if you apply any automorphism, all those properties will get translated in the correct way, and that is what we use to say that adju-v and adju mod x are this is the polar decomposition of adju of x. So why I am saying this is, if you go back to this corollary, so I'm saying if x in equals x star in M, sorry, if x equals u mod x is polar decomposition, and x belongs to and x in B of H, then I am saying that x belongs to M if and only if, I call it V mod x there, let me call it V, if and only V and mod x belong to M. Why is this true? To say that something belongs to M means that u prime x, u prime star equal to x for every u prime in unitary of M prime. So I take any u prime in unitary of M prime, and so this theorem will tell me that if I take u prime x, u prime star, on the one hand, u prime x, u prime star will be u prime v, u prime star, u prime mod x, u prime star. On the one hand, this will be the polar decomposition. On the other hand, this is nothing but x. X in M says that this is equal to x. And to say that if this is equal to x because of the uniqueness of polar decomposition, I am also saying that this is equal to this and this is equal to this. So because of this reason, we find that M is closed under the polar decomposition. And similarly, M is closed under just about anything you can try to do. We proved another theorem that if you have a sequence xi or a monotone net xi of self-adjoint operators in B of H, then we prove, so if xi is a monotone net, in B of H, then we prove that xi converges in has to be SOT to sup xi. That means it is an operator which, as far as the quadratic form is concerned, will give you the soup. So it will convert to that unique operator with that property. Now, if I have a monotone net in M, what will that mean? That will mean that this must also be in M. Because here you have shown that actually it converges SOT to this. And SOT limits of things in M are in M. Or you can also see it the way that I was saying here, because this is equal to say x is in M means that this equals u prime xi u prime star for any unitary u prime and m prime. And those are as positive and as monotone and net as the initial x's, so they must converge to their soup. But they are the same as the initial x's. So the soup of this will be exactly soup of u prime xi u prime star, which is going to be soup of xi. That means these things are in M means that the supreme operation, which is also natural, is in M. So, and for example, using this we showed that P of M, we said this was a lattice. We said it's a complete lattice. Any family of projections will have a soup and an inf. And that soup was actually written as okay, so by the same token, this is going to be a lattice, complete lattice. Is it clear what I'm trying to do? But exactly the same logic. Okay. Okay. That means if you have any collection of projections in M, their soup is going to be in M. Right? Consequence, if X is in M, then we talked of things called the left support of X and the right support of X. Those where by definition the inf of appropriate collections of projections. The left support is actually the inf of all projections with the property that Px equal to X. So inf of all projections, but why in M? So what to say? They are in projections in M. Why? Because this is equal to nothing but there is the range projection. So let me introduce notation. I'll just write the range projection or projection onto the range of what is this projection onto?
Smallest projection such that ex equals to x.
No, that is the same as onto the range x closure. Range x closure, which is the same as range mod x star closure. Right? But this for any self-adjoint projection, for any self-adjoint operator, if you have a positive operator, the projection on the range of a positive, of A is positive, this is nothing but the spectral projection for 0 to infinity of A. Consequently, since all the spectral projections of an element in a one-Neumann algebra are in the one-Neumann algebra, that was that point I was trying to make here. Because the spectral family is unique, you are even otherwise you know that if you have a self-adjoint operator, each functional calculus is going to land in the one-Neumann algebra generated by x. So if x is in M, then all spectral projections of x will be in M. Is this clear? See, any one E of x, if x is self-adjoint, one E of A, is going to be in the one-Neumann algebra generated by A. So if therefore A and M implies one E of A is in M for all E. And actually this is an only if, because if you know that all these guys are there, then your usual monotone approximation by simple functions will tell you that A is itself a strong limit of linear combinations of things like this. Okay. Okay, here is another important notion. See, if M is a one-Neumann algebra, then so is M prime, we know. And being one-Neumann algebra means it's just SOD closed star algebra. So it implies that M prime is a one-Neumann algebra. And the intersection of any family of one-hour algebras is again one such. Right? So in particular, M intersect M prime is the one-hour algebra, which is usually called the center of M prime. Center of M. Center meaning it, by definition, it is all those things in M which commute with everything in M. And in a group, you say the center is all those things which commute with everything in the group. So this is also a one-hour algebra. And so there is a useful notion here, lurking around here. Namely, you take, so let P be, actually for this it can be any, let P be a projection in the one-hour algebra M. Then one considers the following family. That is, you look at all possible central projections with the property that Z is bigger than or equal to P. Now P itself may not be in the center. P is just some element of some one-hour algebra. I am saying look at all central projections which are bigger than P. There is at least one thing there, namely the identity. So this is a non-empty class, and so I can take the inf of this class. For any non-empty class, there is an inf and a soup. So this is called the actually I prefer this notation. Let me call this Zm of P. So by this I will call this the central support or sometimes we will also say cover of P. It is the smallest central projection which contains P. Okay, here's a little okay. Okay, now let us see what this thing, what it means to say this. Something in the central, to say your projection in the center means that it must be invariant. See, you must always keep this thing in mind. Whenever you have a von Neumann algebra, to say you are looking at a projection in that algebra is the same as saying you are having its range. The range of such projections are going to be subspaces which are invariant for the commutant. Right? So this is the one-dimensional algebra. So to say you have a Z in P of Z of M means exactly that its range is a closed subspace which is invariant under the commutant of Zn. And what is the commutant of Zn? Today, so what is this? Now, if something commutes with the center of M, that certainly contains M. M prime Zm is contained in M, so its commutant will contain M prime. By the same token, Zm prime will contain the commutant of M prime, which is M. Right? So it will contain M prime and M. But this is the one-dimensional algebra. So it will contain the set, it must contain the one-dimensional algebra generated by that set, by that self-adjoint set. This is a self-adjoint set of operators. So the generated one-dimensional algebra is just its double commutant. Now I am saying that the Zm prime is exactly the one-dimensional algebra generated by M prime union M. Why is that? Because to say this inclusion I have already proved. Conversely, I want to say
M intersection M dash is subset of M dash and A subset of B dash.
What is A union B commutant? For any two sets actually, what is A union B commutant? That means it must commute with everything in A union B. That means it must commute with everything in A and with everything in B. So this is exactly A prime intersect B prime. For any A and B. Consequently, this is nothing but, if you take the commutant of this, so the M intersect M prime prime. So if we take one commutant, I just get M intersect M prime. If we take double commutant, I get the commutant of that. So this is exactly the commutant of the center of M. So to say you have a projection in the center of M means that you are looking at a subspace, namely the range of the Z, which is invariant for everything in M prime and for everything in M. The commutant of this is exactly this. To say it is invariant for everything here means that it is If it is invariant for everything in this family, then it will be invariant for everything in generated algebra. So what I am trying to say is that this is, I am not saying this is the most efficient manner. So I want to say that the proposition I want to say that the range of the central support of a position P in M, this comes from M. So what is this? So that means I must, so by definition this is the intersection of all subspaces M, but that M is invariant for M contains P, range P, and M is invariant for M and for M prime. That is what our previous analysis will tell us. I have Z bigger than P, that means its range must contain the range of P, and it must be in the center of M. That means it must be invariant under the commutant of the center of M, which is generated by M union M prime. So what is this? What is this family? Okay. So see, in general, if you have a subspace M, let me call it N, and if I want this, and if M is a mononomial algebra, I want to say, if I want to look at, to say that M contains N and M is invariant for M, for a one-dimensional algebra M. So what does this say? This says it must contain N and it must be invariant for M, means it must contain all things like this. Is that correct? If a subspace contains N, then it has everything in N, and it must be invariant under M. So if you hit it by M, you must land only inside M. So M, it must contain this entire space M. Right? So So this I want to say is equal to because I know that M is going to be linearly spanned by its unitaries. So to say it is this span, closed span, or this closed span is the same. Right? Consequently, so I want to say, coming back here, I want to say that this is equal to I want to take the smallest, so range P, P8, I take range P and I take all things of the form U or even X, UPH, U in U of M, I'm going a little fast here, so let me go slowly. See, to say that it contains range P and is invariant for M means that it must contain this space. What we've said here. It contains the range of P and it will be invariant under every unitary in M. And hence unitary invariant under everything in M. So to say it is invariant for things in M, so this will say so what you can I'm kind of swallowing some steps here. Actually, what I've shown here is that, in fact, what I've shown is that we've shown intersection. So this set is contained in this set. That is, if you have something which contains range P and satisfies the first condition, then it must be in the set this set. So if it's in this set, then certainly it satisfies the first condition, and hence it must be in here. But the point that is being made here, when I say it is equal, is that conversely this set is already invariant under, since U and P come from M. U and P come from M. So I want to say this space is invariant under M prime. If we take an x prime and m prime and hit it on the set vector of this form up xi, x prime up xi is up x prime xi. So that is again in up of h. So this set is invariant under every x prime and m prime, and consequently this is a closed subspace containing the range of P, invariant under M and under M prime, and it is the smallest one. Very clearly it must be there in any subspace which wants to contain the range of P and invariant, be invariant under M. But I am saying this space is already invariant under M prime, and so this is the thing that we want. So the range is all things on the form or less fancy, without going to this unitary thing, you can just say that the range of del MP I need to broaden the unity return to see this. Straight away I can say, look at, if you are in range NMP, then you must be
M dash range.
M range P. M dash will leave rank P invariant. P is in M. And rank P will be invariant under everything in M dash. Okay, sir. What is the confusion? I have subspace, namely range P. I want a subspace which contains that and is invariant under M. So it must contain M range P. And this, because M and P is in M, this whole thing is invariant under anything in M prime. So this subspace is invariant under M and under M prime. So it is invariant under M union M prime, and hence under M union M prime double prime, which is Zm commutant. So the projection onto this will be in the center of M. Or actually you don't even have to go through this whole thing. This is clearly invariant under M, and so the projection onto this must be in M prime. It is clearly invariant under M prime, so the projection must be in M, and so the projection must be in the center of M. So it is and it is the smallest such projection, which is invariant under Neumann diagram. So it is the smallest thing in the center which contains range of P. So I'm sorry for inflicting all this stuff to you, but the point is that the heart of one-dimensional algebra theory is in its projections. They contain the entire story of the one-dimensional algebra. The one-dimensional algebra is generated even as a Banach space by its projections, let alone as an algebra. So the knowledge of its projections gives you a handle on the entire one-dimensional algebra. So one must study the projections to understand the one-dimensional algebra. Okay, so this. So talk about okay. So definition. Suppose you have a subset of each. We say that subset cyclic for them. If the smallest m invariant subspace containing S is the whole space. It's just a set of vectors. Our interest later will be in the case where S is actually a singleton set. One vector, in which case we'll call it a cyclic vector. So we've already been using that language from the first day. So we will talk about cyclic vectors, so we can more generally have cyclic sets. Okay. A dual notion is we say is separating. Separating for them if what it says that it can tell vectors in the set S can distinguish two distinct elements of M. If x, y in M x not equal to y, then if this implies there exists xi inverse such that xi is not equal to y. Right? The elements of the vectors in S suffice to bear witness to distinctness of two elements. They suffice to separate any two distinct points of S. And in general, you say for functions, you say some family of points on the domain of that function are separating for that function if separating for a family of functions if two functions which agree everywhere on the set must agree everywhere. Typically a dense set will be a separating set for a continuous class of continuous functions. So the thing to observe here, the trivial little proposition. Let P be the projection with range P equal to ms. Look at the projection onto that closed space. Then the following are equivalent. In terms of this projection, I want to say first. S is cyclic for n. So what does that mean? That means nothing but other than P is equal to 1. And what is the same as saying that S is separating for M prime. Actually, rather than saying this in this complicated fashion, because we're talking about linear operators, what this says is that A and M, AS is 0, implies A is 0. AS is the 0. If an operator in M kills everything in S, it can only do so by virtue of having been the zero operator. Right? So that is the more natural way to state this condition. What does it mean to say it is separating for M prime? That if X prime kills all of S, see, notice that this ms is the same as the smallest see, the projection onto this is M invariant. Right? So the projection onto this must be in P must be in M prime. Okay? Huh? P must be an M prime. And to say S is separating means that if S is separating for M prime, notice that 1 minus P must kill all of S. Notice that 1 minus P must kill all of S. In fact, it must contain this, kill this whole space, because P is identity on this whole space. So 1 minus P kills all of this. But 1 minus P is an M prime. So to say S is separating for M prime will imply that P must be equal to 1. That is, I'm saying, or what I'm saying is, we have proved that. I'm saying we have proved this statement implies this. Right? Which clearly implies this. If it is separating for M prime, then it is cyclic for M. And conversely, if it's cyclic for M, then it must be separating for M prime by the same law. Because if, so let's prove 1 implies 3. If A prime S 0, for some A prime and M prime, I want to say that A prime must be 0. I am assuming that S is cyclic for M. But that certainly means that A prime MS is 0. Consequently, if MS is dense in H, then A prime must be 0. Being okay. So I think this is probably okay, I think I should start on this next important big theorem. I shouldn't start in the remaining period. I'll just tell you what it says and then we'll look at the proof later. There are two fundamental density theorems in one-Neumann algebra theory. One is the one-Neumann density theorem, which we already proved. If you have a star closed algebra then and unital, then it is SOD closed, dense in its double prime. The second one is this Kaplansky density theorem. I meant to do this when we looked at the proof. Okay, I'll give that as one of your exam exercises. The problem is just looking at the proof and then seeing where you need what and saying something. So we'll come to that later. But so the second density theorem, important density theorem, is due to Kaplansky. Okay. See, what did the one-Neumann density theorem say? If you have a unital star algebra, then one-Neumann says that one-Neumann density theorem says that A SOD closure equals A double prime. But on the other hand, when you start dealing with this topology, the weak topology, strong topology, and so on, we've seen already that on bounded sets, the weak topology is the same as the sigma weak topology. Have we? Or have we not? On the unit, actually, right in the beginning, the first class, we were talking about in fact, the linear functionals which are continuous on the unit ball, which are weakly continuous on the unit ball, are exactly the sigma weakly continuous linear function of the whole thing. So what I'm saying is that for many things, it is important to say that if you take things in the double comitron, they say that yes, you can approximate them strongly by things in A. But for many things, you want your approximation to be bounded. You want things to stay See the problem with these topologies I've already told you, they are not materializable. Have I or have I not told you? I even proved to you why the strong operator topology is not materializable. So you have to deal with nets and so on. And if you take a convergent net, it need not be bounded. And so there are various problems which become complicated. So if I take something in A double prime, I know that I can find a net in A which converges to the in the strong operator topology. But in fact, what this will say is that so what Kaplansky says is Kaplansky density theorem will tell you that in fact if you take the unit ball of A and then take the strong operator closure, that will be that is, if I take something in the unit ball of A double prime, one Neumann already told you can approximate that by things in A. But this says that in fact, if you knew that this fellow had norm less than or equal to 1, you can find a net which converges where everything in the net is norm bounded by 1. So for many technical problems, you will find that this is completely indispensable. You will be able to say that something will converge. For many things, it's enough to look at sequences. That is what the Kaplansky density theorem will tell you.
That one is vectorizable. Unit ball SOT is vectorizable.
Because it is given by a family of seminorms and it is given by a countable family of seminorms. Why? We've already seen, right? A family converges SOT to something, that means that for every vector xi you are saying that this xi xi converges to xi. But it is enough to prove this for xi coming from some total set. So it is enough for you to prove that for some dense set of xi's you have this convergence. So to prove that you have a correction xi in A1 which converges in strong operator topology, because they are uniformly bounded. It is only for uniformly bounded sets of operators that this thing is true. That SOT convergence is equivalent to convergence on a total set. But for example, you can just take an orthonormal basis, there is a total set, it is separable in inverse space, you have a countable total set. So it is enough to take an orthonormal basis xi and demand a xi n and demand that xi xi n converges to xi n for every n. And there is a countable family of seminorms. Consequently, you will have a metric which will give you the description by taking this 2 to the minus n. when this is an orthonormal basis. So what do I mean? P is in of x minus y. I can define this as the distance of x and y. And it is true that convergence in this, there is a metric because you are on the unit ball. These things are all bounded uniformly. That is where the series converges. And there is a metric, and convergence in this metric is equivalent to convergence against each xi and hence against any xi. So in fact, this will say that if you take something in A double prime, suppose it has norm 3, then you can take that over norm 3, that will be in the unit ball. You can approximate that in the SOT by a sequence, in fact, of norm less than or equal to 1, and then multiply by a factor of 3, and it will show that anything in A double prime can be approximated in the SOT strong operator topology by a sequence of approximants, each of norm less than or equal to norm of that limiting thing. If norm x less than or equal to 1, you can find a sequence xn in A, so that xn converges SOT to x, and norm xn less than or equal to norm x for all that. Okay.